And okay, so last week we talked about the descriptive data summarization and distance measures. And so in terms of descriptive data summarization, it's mostly about the statistics, about the data, and start from the simple ones like the minimum, maximum, medium, and the mean. And then we talk about different quantiles and how to use that into the box plot. And then later we also talk about distance measures. So obviously the most common one we're using is called Euclidean distance. There's other ways you can measure distance. And then this week, and we're going to move next to the predictive analysis and mostly about the classification actually and the clustering. And so I suspect some of you would know something about these already. So that's what I created the poll. And I'm going to launch the poll. And I hope you can see the question now. And so this is a multiple choice. And so just pick everything that applies. So the first option is, do you know what the concept of classification is? And then do you know the second option is about, do you know a particular technique called decision tree? And then the third one is, do you know about the concept of and what clustering is? And then the last option is about doing a particular technique called k-means clustering. Okay, and if you could just pick all the options that you know, I'll give it 1 minute. I already have like 6 people voted, so which is really good. 3 more. No, I have. Yeah. And if you didn't know any of those, then that's fine. Just don't select anything. Okay. Gonna end the poll there. And so hopefully, and you can see the results now. And so it looks like most of you knows classification and how the decision tree works. So I assume this is covered in the other module. And then today we're going to still go through this, but because maybe I can go slightly faster because you have some knowledge already. And the second part, we're going to talk about clustering, which is another category of different machine learning techniques. And then cover a few particularly specific clustering methods. One of them is k-means, and there's other ones like the nearest neighbors. So obviously there's less people know about the clustering part. Okay, and that's useful to know. Let me start the slides. Doesn't work. And okay, yeah. As I said, this lecture can mostly talk about classification and regression. And so the classification, I think most of you know what that is. And in terms of regression, and it's about fitting the data into a curve, so you can know what is the relationship between different attributes of the data. And we're gonna talk about that in a bit more detail. Okay, and both of these can be used to do predictive analysis. And so it's analyze the current and historical data to make predictions about the future. And essentially, yeah. And so this can be used to do weather forecast and predicting the results of the football game and predicting results of an election, or try to predict, say, for example, how the stock market would move and try to improve your investment. Okay, and then so it can also be used to assess risk because you can then predict what are the likelihood of different outcomes, and then to use that information to help you to make the decisions in business. Okay. And so there are two types of prediction. And the first one is the classification. So you have the input of the data, and you have the model, which here is called classifier, and then you predict a categorical output. And so essentially, and you have lots of data items, and it will run through your classifier, and then it will decide which category that particular items goes to. And I think the typical example would be, say, and you have 3 different type of cancer, and you have all these patient data, and then you run the model or the classifier, which will tell you which type of cancer this patient has. Okay, and the other one is called regression. And the process is similar. You have the input of your data, and you also have a model. And in this case, it's called a regressor. And these both are models. It looks different, depends on which technique you use. And then the main difference is here, and you want to predict the real value. So you don't predict a category. And for example, you might have the previous stock market price, and you have your model, and you can predict what the price would be the next day or in next week or next month. So you have a real value. And in a kind of similar analogy or similar examples, you might have the stock market data, and you have the classifier. And when you predict, it's not actual in the classification. You don't have the real value, but what you can potentially predict is you can predict whether it's next day going to be increase or decrease the price, for example. Those are going to be the broader categories. Okay, let me just put the attendance code. Okay, someone did. Okay, and these are the more formal definitions of classification problems. And I'm not going to go through the actual definition in too much details. But there's some of the concepts and is important. And so first you need to have a set of objects, and which is called O. And this could be the patient, could be a stock price, etc. And then you have set of, let's say just called patient. And then you have a set of attributes, which are A. So for each patient, you'd have, say, their age, their gender, and the results of different medical tests, say, the blood test results, and so on and so forth. Okay. And then you have a different class. So it could be, say, these, and maybe these are different type of cancers. So you know these patients all have cancers, I'll have, say, for example, lung cancer, but you need to, which type of lung cancer they have. And this is class, so the different types, so type 1, 2, or 3. Okay, and then, so what you want to do is to create a classifier, which is called K here. So if you know all the objects, if you know an object and its attributes, and you can decide which class that is in. Okay, and so this is in some sense, can be treated as prediction problems, for example. And if you know the information about the particular patient, then you can predict, say, what kind of cancer this patient has. Oh, okay, and so yeah. So this is a different slightly different examples where you still have patients, and then you have the name, the age, the size of the tumor. So that's the size of the cancer, not the cancer, just the tumor. and then whether the person has cancer or not. And so, yeah, the tumor just means a lump in your body, and it does not necessarily mean you have cancer. And there is a chance it is cancerous, the tumor, then in that case, the cancer will be yes. And then this is where the prediction part comes in. So we have, this is our data set, or let's say this is the knowledge we have. Now we have a new patient called Jim, that's his age and tumor size. And then is this tumor cancerous, or does he has cancer? Okay, so the process doing this will be, you give the data you already have, whether these people about the age, tumor size, and whether they have cancer or not. And this is the training data. You give it to the classification algorithms or classifier. And then it would build the model. And then you can run this model on some new data, which is not included in the original training data. So in this case, for example, Jim, and then it will give you a classification. So that will tell you whether Jim belongs to the one with cancer or belongs to the one without cancer. And so depends on the classifier or the classification method. And for example, if it's decision tree, and it will give you some kind of rules, for example, and if the age is less than 50 and tumor size is less than 15, then the cancer equal to no. So that means that person doesn't have cancer. And if it doesn't meet these requirements, that means yes. And so in this case, then Jim would meet both criteria, so he doesn't have cancer. Okay, so as I see here, and there's two stages, and the first stage is here, where you use the known data, sometimes called the training samples, to build a classifier. Actually, go all the way here. And then the second, so that's called the model construction. And the second one is once you build the model, you can actually use it to do prediction. So you say apply the model to the data, which you don't know the result, then it will give you a prediction what the result should be like. Okay, yeah. And in the model construction, so you have your the so-called the training set, and which are the data which already they sometimes called labeled. And in this case, whether it's labeled, they will say whether it has cancer or no, doesn't have cancer, usually, and that's the attribute you want to predict. And in the training set, and the answers to these, the attributes you want to predict would have already there. Okay, and then the model itself could be decision trees or say neural networks, and different depends on the type of classifier you want to use. Okay, and then when you use the model, you can use that to predict the data object or the data object, which you don't know what the label is. Okay, and then we're going to talk about a little bit about say how do you measure the performance of the model, and because the model like this, and if age less than 50 and tumor size less than 15, might not be 100% accurate. So we have to measure the performance in some way. So obviously you can just do the percentage accuracy, but there's more complex ways to do that. That's a more kind of comprehensive way to do this. Yeah. And once you know the accuracy or how good the model is, and you can decide whether to use it. For example, let's say if this model gives you 80% accuracy, and then you can decide whether that's good enough or not. Sometimes you're happy to accept certain errors, and that's okay. And in some cases, you can't have any error at all. And so then it's still not good enough. It has to be, say, 100% or 99.9% accurate. before you, then it depends on the actual application. Okay, and this is another simple example, and this is the training data, and this is attribute we want to predict. So we have these are the professors, and there's a title. This is how long they has been at the university. Ooh, and this is whether they are tenured or not. So the tenured is kind of like the American concept. And a tenured professor means the person has a permanent professor position at the university. Doesn't quite apply in UK as all the positions are permanent. Okay, so here I think whether tenured is the label we want to predict. And so we take this training data, we'll give it to the classification algorithms, it will build a model, and then you can use this model to predict new things. In this case, it gives you some rules, say, if rank equal to professor or year is greater than 6, and then tenured equal to yes. So that's based on the data we have. And sometimes you have limited number of samples, and it might not be cover all the scenarios, so the rules might not be fully accurate. Again, so once you train this model or this classifier, and you have a new data item, in this case, it's Jeff, and he is a professor, has been at the university for 4 years, and you want to know whether the person is tenured or not. And you can, based on this classifier, it will say yes, because it meets the first criteria, rank equal to professor, and because it's all, so either of these, if it's true, then the answer is yes. So it meets first criteria, so the answer is yes. Okay, again, so you probably know these already, and just repeating as you're learning, get familiar to the machine learning concept. So this is just not for predictive analysis. I think it's for these concepts applies for and all the machine learning techniques. And so it's important to know whether the model is accurate or not. And the things you want to avoid is you cannot test the model using the data to train it. For example, this is our training data, then the model is built on top of this training data. And then say later on, I want to test the performance of my classifier or the model. You can't use any of these because the model is already seeing the answers for this. So it's kind of like you already know the answers, so it always will be accurate. So in a sense, you can't use, say, Tom or Melissa, their data to test the classifier. You have to use some other data which the model has not seen to test its performance. But for the testing purpose, those data, you need to know the label as well. For example, if you know Jeff is tenured, then this can be used to test the performance of the model. But if you don't even know the answer for this one, whether Jeff is a tenured or not, then whatever the prediction it gives you, you cannot tell whether it's correct or not. And so to do this, and it's usually partition or divide the data you have or the training data you have into 2 sets. And the first one would be used to train the data. So let's say this is all the data you have. So you might use the first 2 to train the model, and then the second 2, the last 2, to test the performance of the model trained down here. And so there's different way to split and between the train and test data. Usually you have more to train and less data to test. And because usually the more the training sample you have, and the better the performance is the model. So most likely, if you use all 3 rows for the training data, the performance will be better than you just have 2 rows. And this is kind of like I don't know, and like as human, how we learn. So usually we learn by example. So for example, if you watch a movie and you have different characters, and then you will know, okay, this is a good guy and that's a bad guy. And the more different movies you watch and you get better feeling, you can almost guess much better from the very beginning which person is good guy, which person is a bad guy. Yeah. And similarly here, so the more samples you have experienced, the better your prediction will be. It works the same for the machine learning classifier. Okay, and then so that's about this. You have the training and test. So you need to divide all the data you have, all the labeled data you have, into the part which you show it to the model, or use that to build the model, and the rest you use to test the performance. And usually, the biggest problem of training any model is you don't have enough data, because these data you have to manually label. Say, for example, and this data you have to go through the list of the academics and you to manually get the information of their year and whether they are tenured. And say this one, for example, is even more difficult. For example, in this case, and you need to get the information about the patient, and this comes in and whether they have cancer or not. So this would have privacy issues. So not everybody can just go to a hospital and say, and get the data about the patient's health information. And also, even you can have access to the data to decide whether the patient has cancer or not. It's not average person can do. So you might need a doctor or specialized specialist to do this kind of prediction. So that's make it difficult to get data. And whereas most of these models, they love data, the more data they have, the better it will perform. Okay, and so this is where the M-fold cross-validation comes in. So you try to use all the data set you have to train the model, but still be able to do some testing. And as we said before, for example, here, and if you partition all the data you have into 2 parts, and then you can only have maximum, say, 3 to train the model, and then another one to test. You can't use all 4 because then you have nothing to test the model. Okay, and whereas in terms of the M-fold cross-validation, so you partition the entire set into M, same size subset. So in this case, we're going to partition into 2 subsets, each contains 2 rows. So Tom and Melissa will be the first set, and George and Joseph will be the second set. And you train M different classifier using a different subset as test and the other subset for training. Okay, and so in our case, in this example, we're going to train 2 models. The first model would use Tom and Melissa as input, and then use George and Joseph as a test. And the second one, we're going to use George and Joseph as input data, and Tom and Melissa as the testing data. So they will see different part of the data. The models will see different part of data. So they will learn different things about the model. So entire data set. Okay, so now you have 2 models. Depends on, you can have 3, 4, 5 models. And then when you actually want to predict something, and you combine the value results of these M classifier. So later on, whether you want to predict one person, if it's tenured or not, and you use the results from both classifier 1 and classifier 2. And so this is kind of like a voting. If both say yes, and there's probably yes, and if both say no, it's probably no. And then if it's the difficult situation will become when one model say yes and the other one model say no. And usually what they do is you will have not an even number of classifiers, they will have odd number of classifiers. So there will always be a majority. So let's say if you have 3 classifiers, 2 models said one yes and 1 model said no, and they will choose yes as a result. Okay, and the next part, we're going to talk about actually the accuracy. Okay. So as I said, an accuracy, it's not just a single number. Okay, and in this case, so it depends on the number of classes you need to predict. So in here, you only have 2 classes or 2 categories, either yes or no. But then, for example, when you're predicting a different type of cancer, you might have 3, 4, 5 different classes you need to predict. Yeah. So let's start with a simple one, which only has 2 classes, and then the classes will be either positive or negative. So there's only 2 classes, and then there's also the prediction would have 2 outcomes, and will be predicted as positive or negative. So then in total, there are 4 different possible in terms of effectiveness or accuracy of the model. And so when it's actually positive, the choice or the answer is positive, and the model can predict it as positive. In this case, the model is correct, or it can predict the model as negative. In this case, that will be wrong. So in this case, it's called true positive because it's predicted as positive and it's true. So that's called true positive. And in this case, it's called the false negative because it's predicted as negative and that's wrong. So it's false. So that's called false negative. And similarly for negative and a negative data sample or data items might be predicted as positive. In this case, it's wrong. So it's called false positive, or it can be predicted as negative. So that's correct. So it's true negative. So, and this whole thing is called a confusion matrix. So you can imagine if you have 3 classes for your data set or for your question, so then you have 3 classes and for the row, and again 3 classes for the columns. So in that case, you're gonna a bigger confusion max, which will be 3 by 3, which is gonna have 9 cells. So as you can see, if you have n classes, you can have n squared different cells for the confusion matrix. Again, so still for the same predictions, you can see in this confusion matrix, these 2 cells and the true positive and true negative are the ones which are predicted correctly, whereas the positive and false negative are the 2 classes which are the prediction is not correct. Okay, so these comes the different way to measure the accuracy. Okay, and the first one is the precision, which is the true positive, which is this one, divided by true positive plus false positive. Okay, so true positive divided by true positive divided plus false positive. And so here, essentially, is all the data items predict as positive, and this is the part of all those predict to be positive, which are actually correct. That give you the precision. Okay, and the recall is the true positive divided by the true positive plus false negative. Okay, so denominator. Okay, so the top part is still true positive, but the bottom part is true positive plus false negative. So that's those two. So these are all the data items that should have been true, that are true, but not all of them got picked up, because some of these false positive ones and are also true, but they missed by the algorithm itself. So these are kind of like two competing goals. Say for this one, and you want to make sure all the ones you predict as true, they are all true. So that means you want to improve let's say you're predicting there are 10 people, you run the prediction on 10 people, and you want to say all those you predicted as true are true. And whereas this one is slightly different, you want to make sure you don't miss out things. So all the things that should be true, you want to including them in the result, but these are kind of two competing goals or opposite. If you want to make sure you don't miss any positive ones, and as a result, you might including something which is actually not. Okay, so that's the trade-off. Okay, and then there's also this F measures, and so it consider both precision and recall, and this is the formula. And so you have the precision times recall times 2 divided by the precision plus recall. So to use both precision and recall, and so that's give you a more rounded evaluation of the performance compared to just consider precision or recall. And this made it a bit easier to compare two different algorithms, because as we said, the precision and the recall are two opposite goals. So some algorithms would have better precision but worse recall, and some algorithm will have worse precision but better recall. But then which one is better? And this one allows you to compare the two, considering both precision and recall. Okay, and so let's say this is kind of more visual way to explaining the kind of the trade-offs between precision and recall. So let's say along the y-axis is precision. The higher on the y-axis, the better, the more precise, the higher precision algorithms. And this side is recall. The higher to the right, the more to the right, that means the higher the recall. And the highest is always 1, which means 100%. So as you can see, usually the curve will be like this. Maybe start from this end. And you can see it can always has 100% recall by just returning everything in the data set. Okay, so for example, if you need to decide who from, say, which person in the data set is tenured. And if you give an answer, say, okay, everyone in the data set is tenured, or everyone in the data set is has cancer. And in that way, you were not missing anyone which actually has cancer because you include everyone. But in that sense, and the accuracy or the precision will be quite low because you're going to including lots of people which does not have cancer in the results as well. At the other end, and it's not exactly one, but you can see, you can say, okay, I only pick one person which I know definitely has cancer and ignore all the others. Then in that case, your precision will be quite high, but you're going to lose, like, missing lots of people which actually has cancer from the data set. So you can have high precision and low recall. And so usually this is kind of compromise or trade-off. So you can see any points on this line, for example, some point here, it would have lower precision, but higher recall compared to this point. And if you want to kind of balance the solution, you'll pick something here. And so what you want to do is you want to move the curve, this line, further out. So ideally, for example, something like this. And then for some point here, if you compare a point here, so if you compare a point here, you can see it has the same precision as the point here, but its recall is much higher compared to, say, the same point on this line. Okay, and then the ideal case is you have something like this point here. It has the highest precision and recall, which is not always possible, but that's the desire, that's the ideal case. So usually it starts like something like this, and you try to push the curves as much towards here as possible. And this is also, and sometimes people measures the performance of the algorithm by measuring the area below the curve. So that will be this part. Let me change. So they want to measure, okay, maybe just use the area below the curve, which will be this part. And you can see this curve would have large area compared to this curve. Pen color. Because it has a little bit extra area compared to the first curve. And then this one, this red dot or this line here has the largest area, even larger area, because it has another bit of extra area compared to this one. Okay. Okay, and so to do the classification, there's many different techniques, and they all give you the same kind of type of results. So you have the input with the person, and they can tell you whether the person has cancer or not. But how to decide this, and then many different methods. So there are decision trees, there's a Bayesian classification, which is probability based, and there's neural network, which tries to simulate how brain works. So at a very low kind of primitive level. And then also support the vector machines. So we're going to talk a bit more about the decision trees and the nearest neighbors classification. So decision tree, the advantage of decision tree is it's actually quite simple and also has quite good performance, and it gives you some kind of rules which you can actually follow, or the human can understand. And whereas, for example, the neural network, which are very popular now, and the results, you don't quite understand why that's the case. Okay, anyway, and for decision trees, so let's say this is the training data we have. For each data items or row or data object, we have the ID, age, auto type, and then the risk. So this is the row or the attributes we want, sorry, the columns we want to predict. And then if you give this one to a decision tree, it will give you something like this, which looks like a tree, except it's upside down. So this is like the root, and these are the branches. So like the upside down tree, that's why it's called decision trees. So the rule would be say, if the auto type is to truck, and then risk is low. And then if the auto type is not truck, and you can look at the age, and if the age is greater than 60, risk is low. And if age is less than 60, and its risk is high. Okay, and for the decision tree, so each inner node represents an attribute. So this is inner nodes, and these, okay, are the so-called leaves. The leaves are the classes, but these classes are not exclusive. In this case, for example, you can have 2 risk equal to low classes and only 1 high. Yeah. And each edge represents a test. So basically, each of these edges is a condition, and only one. So that will be the condition on the attributes represented by the node, this node, the node where the edges start from. And this is usually built from top down, so usually built from here and come down. And then when you're using, you need to use the decision tree, and you can start from the top, and you follow the path, and it will tell you which the result should be. Then it depends on data. This is first, in this case, it would first check the auto type, and depends on whether it's truck or not. And if it's not truck, and you go down this side and then look at age, and depends on age, you choose one of these. Okay, and in terms of how this works, so you, as I said, we start from the root, and you need to decide here. You're gonna pick an attribute. This can be either all the attributes you are available. In our case, this will be age or auto type. So the risk and is what we want to predict, so we can't include that. And this is the ID. We know it has nothing to do with the risk. And the person, whether had high or low risk, has nothing to do with what the ID number is. Okay, and you have to decide, I'm going to first split on age or on auto type. And so there's some so-called split strategy to decide which one to choose. Okay, and then once you choose, in this case, we choose auto type, you do a split, and then you repeat the process at each node. And for example, on this side, and it's already basically all the remaining data points or data objects of the same class. So you don't need to split it anymore. You can stop because they are all low. And on the other side, when it's not equal to truck, so that's these top 4, and you don't still how do I say, they are not belonging to the same class yet. So you need to further split. In this case, you're going to using a different class because you are different attributes. You can't use auto type anymore. The only other attribute is age, and you come up with the rules. Yeah, and after that, and so you would have 1 here and 3 here, and all these 3 are all of them are of the same class, so you don't need to split them anymore. Okay, so this is the same process as before, but applied to just general, the same training and predicting process, but applying to direct specifically to the symmetry. So this is original data. Use that to train the model. In this case, the model is a symmetry. And then you can use the model applied to the data, which you don't know what the class is, and you can use that to predict what the class is. And here, and the particular methods we used is the decision tree algorithms. And here it can be other algorithms like a neural network, which will give you a different model, but the process is exactly the same. Okay, so in this case, it's tried to detect fraud. And so that's what the cheat means, and whether it's yes or no. And you have other attributes that you can use to predict. In this case, whether it's a refund, whether they are married or divorced, and then the income. Okay, and so the first, and you need to decide which one you can pick to divide the collection of the data. Okay, in this case, we pick the refund, and then there will be 1, 2. So for the refund, and it's either yes or no. So we have 3 yes. And for these 3 yes, the cheat is always no. So this is already, you have the same values for the attributes you want to predict. So then you don't need to further divide this. So say, that's to say, if it's refunded is yes, and it's always no for the cheat part. And then on the other side, because you only have 2 possibilities, the other side is definitely. So the refund is no. And you can say for the no's, sometimes it's yes, sometimes it's no. So you have to further divide this. So you can use either marital status or taxable income. But you're going to use refund again because it's used already here. So in this case, we pick the marital status. And you can see for all the people that are married and the refund is no, it says that will be this one, and this one. So the cheat is always no. Yeah. And finally, for those which are not married, or sorry, for those that are divorced and single, they have a mix. And again, then you can divide the remaining ones belong to this category based on the taxable income. You can say, okay, if it's less than 80,000, it will be no. And if it's greater than 80,000, it will be yes. Okay. So that's your final model. And then if you have any new data, you can just follow the path and get your answer. Okay, and there could be multiple trees which would fit the data, and usually depends on what attributes you pick to split. So for example, here it's decided to first split it by whether it's refunded or not. And then you could also start with the marital status. So for if it's married, it's always no. And this would still work. Okay, but give you a slightly different rules compared to this one. And their performance might be different. The performance in terms of the precision recall or the F measures. But you can have multiple trees fit on your data. And that's why it really depends on, so that's, you can intuitively get the feeling, say the more data you have, the more likely the tree will represent, be more accurate. Okay, and so once you train the model, so once you build something like this, and you can apply the model when you don't know the class, you want to predict whether it's cheated, yes or no. And so you have this data. Okay, it says refund is no. So if you go down the tree, it will go down here, and it's married. Okay, and then once here you come to married, you know the answer should be no. Yeah, so you can know the final answer should be no. Okay, and so as mentioned a little bit early, one of the benefits of using decision tree is this kind of results is human understandable. You can see, okay, say how the different attributes affect the results. So you can know, okay, if it's refund or not, always lead. If it's yes, it's always lead to no, no cheating, which is kind of rules you can know. Also, I can see how the incomes affect. So if it's less than 80K, it's no, and greater than 80K, yes. And so these rules are useful, and then useful in the sense, for example, the people can understand, and you can try to see why that's the case. The other thing people can actually use this to check whether the model makes sense or not, and use common knowledge. And because they might want to say, okay, why people have income greater than 80K are likely to cheat. Or they might say, okay, that doesn't make sense at all. So maybe there's something wrong with the model or with the training data set, and people can check. Okay, and so in terms of the advantages or the benefits of using decision tree, and it's inexpensive to construct. So as we see, it's relatively simple and quite fast. And very fast at classifying unknown records. So if you have a new data record, you want to know the class, you just need to follow from the tree to one of the leaves. So it can be very fast. And easy to interpret for small sized trees. So if the tree is not very big, like the ones we had here, essentially you don't have too many attributes, and it's easier to understand. If you have dozens or hundreds of attributes, it becomes much harder. Okay, and also accuracy is actually quite good as well. Actually, for a long time, the best performing classifier is I think, forest. I forgot now what's the name for it. And it's using a number of decision trees and use voting. Okay, and this is another type of classification, which is called nearest neighbor classification. Okay, and it treats each data point as a feature vector, and essentially, so each row, it has multiple attributes, and you can treat this as like a points in a high dimensional space with each attribute is a dimension. And the main idea is to assign the class to the points that are nearest to it. So let's say you have 10 points, which you know what their class are, and you have the 11th a new point, you can see which points are close to it and use that as to assign class. Okay. And you might consider not just one, you can consider more than one nearest neighbors, because these are the points which are closest to the one you want to find out in the class. Okay, and so this is related to the distance function. So you can use all the different distance functions or metrics or we talked about before, can be Euclidean, the Manhattan, and some other ones. And you need to decide how many nearest points you want to consider. I think we have some examples later on. Okay. So let's say this is all the data that we have. And in this case, there's only two classes or two categories, either positive or plus, or negative is minus. Okay, and then this new point, this one point here, is the one we want to know what its class should be. Should that be plus or minus? We don't know yet. So the idea will be we're going to look at the points close to it and then decide its class. Okay, so if we only look at the nearest neighbor, so in this case, the nearest neighbor would be this one. And so then in this case, we'll say the class of this point should be plus. Okay. But also, you can say, okay, I'm going to consider 5 nearest neighbors and then decide what the class this one should be. So that will be this one. Then you can see within this area, or within these 5 nearest neighbors, there are 3 minus and 2 plus. Okay, in that case, I can say the class for this one should be minus because I have 3 minus. And here, currently, we just don't know which one is more accurate. And we're just talking about different possibilities to construct the rules. And then even when you're considering 5 neighbors, you can also consider, you can have give different weightings to each of these neighbors. You might say, okay, the ones that are closer to me had larger weight in the final decision compared to the one that's further away from me. So for example, and this plus is very close to me, so it has much more weight affecting my class compared to this one, which is further away from me. So it should have less weighting in the overall decision. And in that case, you might still, the overall class might still be plus, because even you only have 2 plus, but they are much closer to the point compared to the 3 minus. Yeah, again, so there are just many different ways you can decide. So the 2 important things to decide is, and how many neighbors you consider, is that 1, 2, 3, 4, 5, 6, 8, 10, 100, anything? How many neighbors you consider? And then how do you decide? So you can say each neighbor has equal weighting, or the one closer has higher weighting, or some other rules. So these are 2 things you decide for the k-nearest neighbor. Okay. So when you choose how many neighbors, and if it's too small, then it will be very sensitive to outliers. For example, it just happened to be an outlier. So there's this red dot in the middle of the black class. And you would say most likely this one should be black because it is a black class, but it just happens to be close to be a red outlier. So if you only consider 1 neighbors, and then make it, you will probably say this should be red. That's what it means, the sensitive to outliers. And if you have 2 larger k, and you can including too much data point, which may, how do I say, kind of say in the worst cases, including everything from the entire data set. That's not very useful to decide which class that need to be, like this case. So if you choose the biggest neighbor here, including everything in the data set, then it's the same for every point. There's not much, it doesn't really help you to decide which class this X should be. So usually you pick somewhere in between. So it needs to be bigger than 1, but also less than the entire data set. Again, so there's no fixed rules say what this number should be. But as we said, it usually shouldn't be 1, should be larger than 1, but also not too large. And then what is too large, that depends on your data set. Okay, and so some of these kind of properties, or the advantages or disadvantages of using k-nearest neighbor. Okay, and so it's a local method. In the sense, you only need to consider the data points close to this one. You don't have to consider the entire data set. And it has quite high classification accuracy in many applications. So that's just general how it works. And also it can be easily adapted to new training objects. Okay, so once the functions change, so what you want to classify as different, that's quite easy to change. Okay, and the problem is it can be quite expensive. So it requires k-nearest neighbor query itself can require you go through the entire data set. So what this means is if we want to find, let's say, the 5 nearest neighbor of this X in the entire data set, in the worst case, you actually have to calculate the distance between X and all the other points, and then pick the top 5. That itself, if you have lots of points, that can be quite expensive. And also, it does not generate explicit knowledge about the class. So you can say, okay, the class of this X should be black, but it doesn't quite tell the people what kind of criteria makes this one black, except this one is closer to the others. That is not something you can translate into a general knowledge about, say, what make a point black or red. All you can say is just because it's close to the existing black, but you don't know why. Whereas, say, compared to the symmetries, and they can actually tell you, okay, whether it's married and income levels, those are the criteria which actually made a difference. Okay, we also have a few slides and last a few slides about the regression. And as I said, regression is about predicting a value instead of a class. So the similarity would be, you also need to first construct the model and then use the model to predict unknown values. And you can do simple or multiple regression, or you can do linear or non-linear regression. The main difference will be the classification. The output is a class or bin or label, whereas the regression gives you a value. Okay, so So linear regression is probably the easiest one. So essentially, you try to fit a line through the data set. You say, okay, I can use one line, straight line, to describe the data set. That's how the trend in data is. And you can have simple regression, which only using one other variable. So you're going to use just X to predict Y, 1X, or you can have multiple regressions. So you have multiple X's. So in this case, X from 1 to D, so that D different variables to predict Y. So that's a multiple regression. And the other term you need to know is the residues. That will be difference between the predict and actual value. So usually the smaller the residue, the better the model, the more accurate the model. Okay, and let's say these are the points we have. And so we want to use this one, do a linear regression. So this is the line we want to predict. And you can see there will be some distance between the actual value, which is where the y-axis or the y-coordinates of these points are, and the predicted value. So the predicted value, because it's a straight line, you can try to change the position and angle of the line, but it might not always give you a perfect fit. So there will be some distances. So obviously, the smaller the total of these, the smaller the total of these distances, the better. So that's the algorithm to find the linear regression is to find the line which has the smallest total distance. When you add these red lines together, the smallest one. In this case, using squared, so whether it's positive or negative doesn't matter. Okay, I'm not gonna get into the actual details. How do you find this line once you're given these points? Yeah, and in most of these packages now, you just need to select the linear regression that they will do this for you. Okay, and in terms of the advantage of linear regression, and it has very solid mathematical foundations. So it's very clear exactly why you want to do this. And it's simple to calculate and to understand for moderate number of dimensions. So if you don't have very high dimensions, in terms of calculating the distance between the points and the regression line, or if it's a high dimension, it might actually equivalent of a service. It's quite straightforward to do, at least conceptually. And in many applications, it has quite good performance. And it really depends on the actual nature of the data. So if it's actually, there's a linear relationship between the y and the other dimensions, and then it would work well. But if it's not linear, for example, and the y increase exponentially, and then in relation to x, then a linear regression is not going to give you good results. Yeah. And as I said, but actually many dependencies are not linear. Either can be, say, quadratic, cubic, or exponential, or even, say, what is the inverse or square root or something. Yeah. And also the model is global, so you can only really have one line for the entire data set, whereas sometimes the model might compare and include it as different subset. They have its own models. Okay, that's it. That's it for today.